If you've ever spent 30 minutes shifting between lines at a DMV or tax office, you know how quickly an unmanaged system can stall. We can address this using simulated annealing, a Python-based model that searches through thousands of possible job assignments to find a near-optimal schedule. Download the script linked below and open your code editor. The logic we are setting up today is flexible. It applies whether you are routing hospital beds, IT support tickets, or government services. By the end of this video, you will have an automated tool that takes a list of disorganized service requests and organizes them into a balanced workload. Let's look at the top section of the code. This is where we define the core algorithm, simulated annealing. Think of this algorithm like leveling out sand. You shake an uneven tray until the material settles flat. Similarly, the Python script generates random assignments, cooling down the search to find an evenly distributed workload. To measure the efficiency of our schedule, the script tracks a metric called the makespan. Makespan is the total time it takes for the last counter to finish its assigned work. By minimizing this number, we ensure no single worker is stuck with a massive backlog while others sit idle. Scroll down to the scenario description variables in your script. We've set up 3 offices, 5 total service counters, and 12 citizens waiting for service. Each citizen needs between 2 and 4 services processed, such as tax payments, permit applications, or general transactions. To make this realistic, we've included a skill multiplier. This accounts for the fact that a specialist might handle a specific task faster than a generalist. A multiplier of 0.8 reduces the base processing time, representing a faster worker. A multiplier of 1.2 increases that time, representing someone who is slower or less experienced with that task. Designing these specific constraints and skill sets allows the script to model the actual dynamics of your office floor. Run the script now to see our baseline. As the simulation finishes, the terminal will display how those 12 requests were initially sorted. Look at the section of your output titled Final Workload per Counter. This data shows the total minutes each counter worked and provides a list of exactly which citizens were assigned to them. In this terminal view, we can spot the bottleneck. This counter has a significantly higher workload, meaning it will be the last one to finish. Let's try to eliminate that bottleneck by adjusting the resource parameters in the code. First, go to the configuration section and add 1 more service counter to the suburb office. Second, we'll simulate staff training. Find the permit application multiplier for that overburdened counter and lower it from 1.2 to 0.1. Save your changes and run the simulation again. Our original make span was 240 minutes. After these changes, the time until the last counter finishes dropped to 160. By lowering the multiplier, the algorithm shifted more permit applications to that newly efficient worker to balance the load. By adjusting these parameters, you force the search algorithm to find a solution that reduces idle time and balances the effort across your entire team. You have now successfully built a dynamic model that uses data to identify and instantly resolve service bottlenecks. This simulation provides the logic you need to justify operational changes, whether you are requesting budget for a new hire or identifying which staff members need more training. You can now adjust the variables in this script to reflect the specific constraints of your industry, from healthcare triage to logistics routing. Effective optimization helps create a more sustainable pace for workers and a faster experience for the people they serve. Like this video, subscribe for tutorials, and share how you're using this script in the comments.